Okay, so I will talk about today. I'm gonna talk about Higgs bundles on elliptic surfaces and the logarithmic transformation. So, yeah, this is based on joint work with Ludmil Katzarkov. So, okay, let me start. So let me begin with the very basic things. So let X be a smooth projective variety, and let H be an ample line bundle or divisor on X, and maybe ample divisor. Maybe ample divisor on this variety X, and the E is a torsion-free coherent sheaf on X. Then, yeah, we can define so-called slope of this torsion-free sheaf as it's quite well known, but anyway, it's the first chunk class of E times H to the dimension X minus 1 over this length E. And yeah, and so I mean, most of the time we will talk about vector bundles, but anyway, vector bundles on X, but anyway. And then this E is mu semi-stable or mu stable if for any this non-zero shift in E, we have this inequality. So if this is true for any non-zero subshift, then we said this mu is semi-stable. And when this strict inequality holds, then we will call this is mu semi-stable as well known. And yeah, so this is this notion appears in many contexts. For example, when I consider this GIT quotient and this when you want to construct a moduli space of shapes, some certain vector bundles. These notions are very popular notion, appear everywhere. And for example, so anyway, but this notion also has several other contexts. So appears in several other contexts. So let me mention one of the most fundamental theorem in this field by Narashman and Shashadri. So when this X is a smooth projective curve, so this is smooth projective curve, and then in this case of vector bundle E on C is mu stable. In this case, we just call it stable, but anyway, mu stable if and only if E comes from irreducible, unitary representation of fundamental group of C. So this is one of the most fundamental theorem in the field. Anyway, so when a vector bundle comes from this unitary representation, then it is stable, and we can prove it on both sides. So, indeed, this theorem, as I told you, is really one of the most fundamental theorem. And yeah, we have several variants of this fundamental result. So for example, when I consider this curve, so the Riemann surface, and then let me assume that there are several puncture. And then in this case, this fundamental group of C minus this point P1, P2, Pk. So when I consider this complement, then the fundamental group is nothing but generated by alpha 1, beta 1, alpha g, beta g. And I choose a point and I choose a cycle here. So gamma 1 to gamma k, such that this gamma 1, this alpha 1, beta 1, alpha 2, beta 2, alpha g, beta g, and gamma 1 to gamma k is trivial. So I can consider this a functured Riemann surface, and sometimes I can consider OB4. branch over this point. Then this OB4 the fundamental group of this Riemann surface is nothing but C is nothing but same as this alpha 1, beta 1, gamma k, having the same relation, and this gamma 1 to the m1 is equal to gamma 2 is m2 is equal to gamma k, mk is equal to 1. And then we can consider a similar version of this. We can consider this OB4 fundamental group and consider its representation, and then being motivated by this, this Narashima and Sheshadri theorem. So Mehta and Sheshadri introduce so-called parabolic bundle. So let me give the precise definition here. So being motivated by this representation of this OB4 fundamental group, they introduce so-called this parabolic bundle over this curve. So yeah. So again, C be a smooth projective curve, and this P is a bunch of points, so K points in C, and let M be this. I collect this M1, M2, Mk. So this is integer M1, Mk in G. So this the right notion is this Mi is integer. And then a parabolic bundle vector bundle on C with a parabolic structure at for example, sorry, I just consider one point, but we can easily generalize this to this K point. So anyway, I consider this Riemann surface and choose one point P here. And for this case, a parabolic vector bundle on C with this parabolic structure at this this point consists of vector bundle E with a flag flag EP. This is nothing but this 0, starting from 0, and this E1 and EFR EP, which is EP. So I mean, I consider vector bundle on this Riemann surface, and then for this point, I choose this EP, and there are some flag on this vector space. So this data consists, this data gives me a parabolic vector bundle C on C. And for each R, I can assign so-called weight, and the weight alpha I, which belongs to the real number, assign to each subspace this Fi EP, such that this 0 alpha 1 alpha R is less than equal to 1. Okay, is there any question? No. Okay, anyway, then, I mean, I can generalize the previous Narasimhan-Sheshadri theorem. So this parabolic, I can give certain stability condition on this parabolic vector bundle. And then one can show that this parabolic vector bundle is stable or semi-stable when this comes from this unitary representation. So, I mean, in this case, I can define parabolic degree of this vector bundle. And this is nothing but the degree of E plus a little complicated formula, alpha I times dimension Fi EP modulo Fi minus 1 EP. Anyway, I have this notion of certain parabolic degree, and then using this I can define stability. And a version of Narasimhan-Sheshadri theorem here. Sheshadri type theorem. I think basically, I mean, Meta and Sheshadri, and also, yeah, I found this in paper in part. Okay, so anyway, I can define this notion of parabolic bundle, and one can generalize previous story. Any question?
So,
yeah.
this flag for every point that flag has to be the same one.
I mean, indeed, we can change the. I mean, it doesn't have to be. So, I mean, right. So, I mean, how can I say? If I consider this length R vector bundle, then I consider this full flag. But sometimes it doesn't have to be different. I mean, sometimes I allow this space is same as this space. So, I mean, this inclusion is not strict inclusion. Yeah.
And can that vary from point to point? One marked point has a flag of different nature of the other point?
Yeah, that's also possible. Yeah. Thank you. Okay, so then anyway, I can define this this parabolic vector bundle motivated by this result, and one can also, I mean, there are another generalization. So this is where this Higgs bundle comes. So you can, I mean, so there's another direction. to, another way to generalize this result. So anyway, this is the Rashman and Shashadi theorem consider this representation, this unitary vector bundle. But we can also generalize this structure group to arbitrary general linear group. So I consider this representation, and this gives me the notion of Higgs bundle. So let me write down the precise definition. So let X be a smooth, again, projective variety, or just algebraic variety. And H is again an amplitude divisor on X. And E is a vector bundle on X. Then a Higgs field is on X is Higgs field on this vector bundle E is a morphism phi from E to E tensor omega x1 satisfying this phi, which phi is 0. So this is just the notion of Higgs bundle. So then again I can define similar stability conditions. So this Higgs bundle, so I consider this pair to be Higgs bundle. So a Higgs bundle E and phi is semi-stable if for any, again, subshift E prime in E preserved by phi. By this means I have this subshift, and I again have this subshift, and preserving means that when I restrict this map to here, then this maps to here. So this is the definition. This is what I mean by preserved by phi. And then we have, in this case, we have this rank E prime and C1 E prime. This H depends on X minus 1. This is nothing but mu E prime is less than equal to this mu E. Yeah. And then, in this case, we can also generalize the, I see. Yeah. Okay. So anyway, in this case, this Higgs bundle is semi-stable if this inequality holds for any subshift preserved by phi. Okay. So I will repeat the question from now on. Sorry for, yeah. I just saw the comment in the chat. So yeah. From now on, let me try to repeat the question time. Anyway, so there is a theorem by Simpson. So one of the most fundamental theorem here. So this it proves that this S equivalent classes of semi-stable rank R Higgs bundles of with anything Chern classes. This set is, there is one-to-one correspondence between this S equivalence of this semi-stable anchor Higgs bundles with the vanishing classes with this Jordan equivalent class of this representation of X to GLRC. So this is, I mean, another variation of this Narashima and Shishadri theorem. So yeah, anyway, this considering this representation of this fundamental group, I mean, gives me lots of generalization of this notion of vector bundle in this case. And yeah, let me not give the definition, but we can also generalize. I mean, there are another, how can I say, another variant of this notion of vector bundle. So we can also generalize this notion. I mean, we can also define the notion of a parabolic Higgs bundle. Higgs bundles. So let me not give the precise definition, but anyway, we can also, I mean, this is kind of a generalization of this parabolic bundles and this Higgs bundles, which is again the generalization of this ordinary notion of vector bundles. So anyway, we have this, we can generalize this notion of vector bundle motivated by this representation of fundamental group. Okay, is there any question?
Sorry, so if
Yeah.
usual symmetrical bundles occur are one correspondence with unitary representations, then parabolic bundles without the Higgs,
Yeah.
they are in correspondence with what?
So they are representation of this obifold fundamental group. So I mean, I consider this obifold fundamental group.
Literally that, or unitary? Or
Yeah, unitary representation of this ordinary. I mean, sorry, unitary representation of this obifold fundamental group. That's the parabolic bundle. Yeah. So I consider this. Thank you. So I mean, I have this variety, and then I have again divisor, and then I mean, how can I say? I consider this vector bundles on this space, and then I have a map from E to this E, tensored by this omega 1. But in this case, I mean, there are still a little, I mean, for literals, I mean, there are several various definitions for various literature, but some people use this log divisor. I mean, I consider divisor here, and then I consider this log, how can I say, one form with log 4 at D, and then I consider this Higgs field in this case. And then I can generalize this notion of, I can still simulate and generalize this notion of a parabolic bundle and Higgs bundle at the same time. Sorry, I mean, the question was, how can I say? I think the question was basically asking the definition of this parabolic Higgs bundle, right? Okay. Do you want me? Sorry. There's also flag. So let me. How can I say? Just write down the definition. I mean, it's not hard, but I mean, okay. Just 1 minute. I wrote down the definition somewhere, but I mean, yeah.
Now you require the morphism to preserve not the but the flag.
Right. So there is some mixture between this flag here and flag, but again there is kind of Griffiths transversality play a role here. So I mean, I just Fi E maps to Fi minus 1, I believe, maybe something like this one. Some condition like this holds. So yeah. So anyway, that's the definition of this. So anyway, the question is the definition of what is the definition. How can we generalize these two notion of vector bundle to define parabolic Higgs bundle? And what I said is that basically, I mean, the definition of parabolic Higgs bundle, I consider this the Higgs field is, I mean, a map from E to E tensor this one form with log 4 at this divisor D. And this, how can I, and then another question is how can you generalize this parabolic? And then I said that, okay, then at D, I consider this filtration. And then, I mean, I consider this filtration, and this map should be, in a sense, compatible with this black. That's all we discussed. Is there any further question? Okay. So anyway, yeah. This is I mean, this is the notion of. Anyway, I discussed this generalization of this vector bundles on this. Yeah, there are several very generalization of this notion of vector bundle. Basically, I think motivated by this Narashima-Shishadri theorem, considering this representation. Okay, then the topic, I mean, what I want to discuss is these Higgs bundles on elliptic surface. On elliptic surfaces. So let me, I mean, I think everyone knows the definition of elliptic surface, but let me just write it. So on elliptic surface, S is a focus surface with elliptic fibration. I mean, so fibration phi to S to C. So this elliptic fibration means that a proper elliptic fibration means a proper morphism whose general fiber is a smooth curve of genus 1. Okay, anyway, I want to discuss these Higgs bundles on this elliptic surface. And I mean, there are a fundamental operation on this elliptic surface introduced by Kodaira in 1960. So this is so-called logarithmic transformation. So let me tell you what it is. The idea is quite simple. So I have this surface S, and it maps to this curve C. And then I choose a point here, P. And then I consider a small neighborhood, delta, which is, I mean, I consider this, small neighborhood around this P, defined in this way. So this is a small disk containing P. And then I have considered the inverse image of this surface. I will call this as delta, which is pi inverse delta. And because, you know, because this is the elliptic fibration, okay, sorry, I forgot to mention one thing. So I consider this fiber, and this, let me denote this fiber FP, and then let me assume that this is a smooth curve with genus 1. Smooth projective curve with genus 1. So anyway, let me assume this fiber is a nice curve with genus 1. And then, anyway, I consider this, this one. And then, in this case, this S delta, this is delta times, because, I mean, in this small neighborhood, if I choose this delta to be sufficiently small neighborhood, then this is nothing but delta times C model G2. I mean, because elliptic curve always has this uniformization. Well, this G2 acts on this delta times C this way. So this N1, N2, that this XZ, this is coordinate for delta, this is coordinate for C. This is nothing but X plus Z plus N1 plus, plus N1 plus N2 X. So anyway, I can define this this action, and then, I mean, in this case, we can decompose this surface. So I have this inclusion, and for this case, let me write this. Sorry, this is C. This is C, and this is C. P, and I have this. This is nothing but pi inverse this C P. Okay, then what I do? So in this case, okay, and then let me choose a point. So this, let gamma x be a point of order m in this fx. So well, this is C quotient G plus this G. So I mean, for each x, this fiber is an elliptic curve, and then I choose a point whose order is, a point is order m. So then, in this case, so yeah. Yeah. So I mean, yeah. The question is, what is this W, right? What is W, right? So W is, this. How can I say? So for each fiber, the question is what is W, and this for each x, this fx is elliptic curve. So this is C modulo certain lattice, and I can just I mean what you said is correct. I can identify this fx is C quotient Z plus some, how can I say, this is just the integer, and I mean this is just, I consider there's certain function, so which maps to C, and then for each point I have this function, and this is just
You're not saying the integration is locally trivial.
Yeah. So yeah, there's no guarantee there. I mean, in general, it's not true. So the fiber can vary, but I can control this fiber in this way. Yeah. Thank you very much for the question. Okay. Anyway, then I can consider this gamma x to be a point of order m in this fiber, and okay. So for convenience, we choose a base of this lattice. We can assume that this m times this gamma x is always q, where this q belongs to n, and this GCD of this q and m is trivial for all Is there any question? Yeah, the action is trivial on delta. So yeah, the question is whether the action is trivial on delta. Yeah, the action is trivial on delta. Sorry. Right. Right. Yeah, the first they do not act on the first component. They just act on the second component. Right. Thank you. And then, I consider this delta tilde, which is again this operation, and I consider this, how can I say this, x minus p is less than equal to epsilon 1 over m. And anyway, I can define this delta tilde, which has this M2 map to this delta. And then, please remember this diagram. Yeah, so so I do not touch this part. The logarithmic transformation is an operation which I don't touch this part. I just replace this, how can I say, this part by certain, this, so I consider this M2 cover, which is branched over this origin. And then I construct a certain surface, certain new elliptic surface here. And then, how can I say, I will construct a certain new elliptic surface here. And then, yeah. So I will explain this in detail. But anyway, this logarithmic transformation is an operation replacing, so manipulating this part. So I obtain a new surface Sm over C. So as I told you, I do not touch this part at all. So this is the same as before. But here I consider this surface and manipulate this surface in some way. So I consider some new surface which is isomorphic. I have this new surface, but over this, except this origin, except this origin, this new surface is this new vibration will be the same as the previous vibration. So I can identify this one. So okay, so I will explain in detail, but anyway, the point is that so in this family, I consider this M2 map and obtain certain surface, construct a certain family of elliptic vibration, and I do some kind of operation to find the new surface F delta. And the point is that over this, this functional disk, this surface and this surface are isomorphic, analytically isomorphic. So I can identify, I can remove this part and glue this surface with this surface to obtain the new surface. So that's the logarithmic transformation. So anyway, let me give you some detail. But anyway, that's the basic idea. Okay, is there any question? No. Okay, how can I say? The construction is quite critical, but anyway, I consider this new surface, which is this delta tilde is this one, and this delta tilde times C, and I model out this by G2 plus G over mg. So, well, it's G2 plus G mod mg acts on this delta times C by this N1, N2, K, and this X and this J is nothing but this e to the 2 pi I K over M X tilde and Z tilde plus N1 plus N2 plus, N2 W dm plus kq over m. So I mean, how can I say? I can't. Okay, let me go back. So I mean, sorry, I'm writing a little confusing notation, but anyway, so I consider this M2 uncover over this delta, and then I define this F delta tilde in this way. So this is nothing but this F delta tilde, F delta, I delta tilde times this C modeled by this group, where this group acts on this this vibration, this trivial vibration, C vibration, and then I model out this by this way. Then, yeah. So by this way, I obtain a new surface, and then this surface is, as I told you, I obtain this new surface. Sorry, this is the tilde. So delta tilde. And then this surface is, yeah, this surface is isomorphic to this previous surface over this function disk. So I can glue this surface with this surface, so obtain a new surface Sm. Okay, is there any question? So anyway, this is a very analytic operation. So I mean, yeah, this is not an algebraic operation at all. So this logarithmic transformation, as I told you, is quite wild operation. So it, for example, it doesn't preserve this the class of Kähler manifold. What I mean is that if S is Kähler manifold, can you Kähler surface? I mean, if this is elliptic, I consider this elliptic vibration in the if this is Kähler surface. But if I do this logarithmic transformation, and sometimes this surface, this new surface is not Kähler anymore. So this sometimes make this algebraic surface into non-algebraic surface. So this is quite wild operation. But I mean, so this how can I say? One annoying thing as an algebraic geometer is that this operation is quite wild operation. So I cannot this new surface I obtain is not algebraic anymore. So yeah, this is very wild operation. But the good point is that, I mean, general, how can I say, elliptic surface. Sorry, and then let me mention one more thing. So, but what is the effect? So I mean, okay, I should mention this one. So I consider this elliptic surface. And then I do this logarithmic transformation to obtain a new surface. And the key point is that, I mean, over this point, this is just an elliptic curve. But then after this logarithmic transformation, what happens is that this fiber is no longer this fiber become multiple fiber. This fiber become this multiple fiber of order m. Okay, this operation. I mean, this operation. I'm sorry. I'm a little fast here. So anyway, so this operation makes this fiber into a multiple fiber. Yeah. Yeah. The question is whether this fiber is non-reduced, and this is true. Yeah. So.
The function is the same right here.
Yeah.
Just changing one fiber.
Right. So
the
yeah.
Fiber is something analytic, but yet not.
Yeah. I mean, how can I say? Yeah, that's possible. I think. Yeah. I mean, how can I say?
I mean, by non-reduced, I understand.
Yeah.
A scheme where the
Yeah.
like the topological space is the same as this one, but the
Yeah. Yeah.
The logic is still like one thing, but more like from the equation.
Yeah. Anyway, the question is, I mean, how can I say?
No, I was wondering like what we mean exactly by
Yeah.
diffuse.
I mean,
multiple fiber.
I mean, yeah. That's okay, let me. Okay. Anyway, sorry. So I mean, the question was, I mean, how this become? I mean, maybe what I can say is that the question was how this, what I mean by this multiple fiber would M, and then what I can say is that anyway, I consider this vibration, and then I mean this vibration, this is linear system over this space. And this again, I mean, let me consider another point here, and this is this I give this linear system and this FP and FP prime. These are all belongs to this linear system. I mean, if this is P1, for example, if this is P1, then this gives me the same linear system. But in this case, this Fp prime still gives me this linear system on this new elliptic surface. But in this case, this Fp prime is still here. But this fiber is now become, this gives the same vibration. So I'm this new vibration, and I consider this new fiber over this P, then this M times Fp gives the same vibration. So that's the effect of this logarithmic transformation. So anyway, so how can I say, this is very powerful operation introduced by Kodaira in 1916. So, but this is very, as an algebraic geometer, this is still quite mysterious operation because sometimes, makes this algebraic surface into non-algebraic surface, and basically it's an analytic operation. And sorry, I'm a little running behind, so let me go further faster. So anyway, the key point is that general elliptic surface. So general elliptic surface can have many multiple fiber. But whenever this multiple fiber is smooth, then can be obtained by this logarithmic transformation on elliptic surface without multiple fiber. So in this sense, this is very useful operation. So for any, how can I say, elliptic surface, I can certainly deform this surface to make this surface into, these multiple fibers are all smooth. Then I do this logarithmic transformation to make this surface elliptic surface in. I obtain this elliptic surface from an elliptic surface without multiple fiber. So this is very powerful and useful operation in, for example, topology and differential geometry. This is extremely useful operation, play a really important role in many branches of mathematics. But anyway, I will not discuss this today. So anyway, we have this elliptic surface. Then, okay. So as I told you, this logarithmic transformation is extremely powerful. Powerful tool. But the problem is that this is basically an analytic tool. So it's very hard to as an algebraic geometer, it's very hard to see what happened. So in in the level of algebraic geometry. But anyway, there's a theorem by Joubert. So he constructs certain transformation which sends this some vector bundles on S with certain condition. Sorry, let me just mention in this way. So let me just state the theorem in this way. So he obtained a method to make a vector bundle on this surface into a new vector bundles on this surface obtained by this logarithmic transformation, again with a certain condition. Sorry, So anyway, he developed a method. As I told you, it's extremely hard as an algebraic geometer to compare this surface and this surface in an algebraic geometry way. But anyway, this Joubert construct a functor from here to here and here to here. He basically describes some analytic functor. So this analytic operation which sends some vector bundle here to vector bundle here and vector bundle here to vector bundle here. And there is one more theorem I need to mention in order to, how can I say, state the main theorem. So there is again another type of result by Bauer and the result generalized by Bama. So let's see, in this case, let's see the smooth curve, projective curve of genus greater than or equal to 2. And then what they prove is that they consider this this category of this category. So this is the category of H. H is again this some ample divisor on this surface. So I consider this elliptic surface. Sorry, I consider this elliptic surface, and this H is ample divisor on this elliptic surface. Then I consider some category of this H semi-stable Higgs bundles on S with the second chunkless is trivial, and the determinant is a vertical divisor. Vertical divisor means that this determinant is a line bundle and it's supported on this fiber. That's the definition of this vertical divisor. And for this, they consider another category. So this C, K, M is parabolic Higgs. So I didn't give the definition, but there's parabolic Higgs bundle on this base curve. So so this surface can have several multiple fiber, P1, P2, Pk, and this order of multiplicity is something like M1, M2, Mk. And then I consider, so anyway, this order and this point where these multiple fibers are located gives me this data, this P, and this is point, and this is this multiplicity. And then I consider this category of parabolic Higgs bundles. So this is the category of this parabolic Higgs bundles on C, and this data is given by these two data. And what they prove is that indeed there's natural equivalence between this category, this vertical Higgs bundles, and this bundle, parabolic Higgs bundle. Okay, is there any question so far? And then, okay, so there's another some more condition. This error characteristic is something like positive, some condition like this. But anyway, okay, then let me write down the main theorem and finish this talk. So the theorem I want to talk about is to myself and Katzarkov, saying that so this operation, as I told, I mean, you know, for this case, this okay. Well, let me give the detail and let me explain. So as I told you, this Joubert found two functors which sends this vector bundles on S to a vector bundles on this SM, and the vector bundles on SM to vector bundles on S. And by theorem of Bauer and Balmer, we can identify some vector bundles on S with parabolic bundles on this, base curve, right? So I mean, let me write this way. So I consider this SM over C, and I consider this S, and I did this by log transformation. So let me consider this situation. I mean, I consider P here, and I do already have this elliptic surface, but I do logarithmic transformation over order M to obtain this new surface. Let me assume that these two surfaces are algebraic. So this logarithmic transformation, as I told you, sometimes makes this algebraic surface into non-algebraic surface, but let me assume both surfaces are algebraic in this case. Anyway, then this certain vector bundles with certain vector bundles on S can be identified this parabolic bundles on curve, right, by this theorem. And again, this certain bundles on SM can be identified with the parabolic bundles on C. And what Joubert did is to construct a functor which sends vector bundle here to here and vector bundle here to here. So the natural question is, can he understand these two functors in the language of this base curve? Because I can identify this vector bundle here, vector bundle here. So what I claim is that the two functor Joubert constructed has a very natural interpretation of in terms of parabolic bundles on this curve. This is very natural indeed operation. So this, how can I say? So this direction, this is what we prove is that this direction is nothing but forgetting this parabolic structure. So parabolic bundle is, I choose a point and give some extra condition on this one. Okay, so this direction, I consider this vector bundle can be identified parabolic vector bundle on the base curve, and then this functor is nothing but forgetting this parabolic structure. And this direction also has very natural interpretation. This is nothing but corresponds to pullback, kind of pullback functor in terms of parabolic vector bundle. So this operation was introduced by Joubert in 90s, but what we prove is that we have a very natural interpretation of this Jubes 2 functor in terms of parabolic bundle. This is nothing but this forgetting parabolic structure and this pullback. And moreover, we can, how can I say, explicitly describe how this operation, how can I say, behave in the moduli of vector bundles. I mean, we can describe this operation in terms of moduli space of vector bundles on curve. So yeah, I mean, this operation is, I mean, when I first saw this operation, those are quite mysterious, but the base curve level, it's quite easy to understand this operation. We are trying to find some application of these two operations using this language of vector bundles on curve. Okay, that's all I want to say. Thank you. Thank you very much. Is there any question?
Sorry, so it's representing the category.
No. So yeah, so okay, let me first, the question was Jubes functor are equivalence of category.
And you write just 2 arrows and instead of 1 double arrow, so I guess like there's something there.
So, but my answer is this category and this category are not equivalent. So I mean, for example, you know, when I consider this moduli space of parabolic bundles on this curve, then this gives me an extra structure on this fiber, right? So I mean, when I have a bundle here, and this bundle has this, you know, there's some flag on this fiber, right? So indeed, this category is much bigger, kind of. So I mean, this functor is kind of subjective. I know, very kind of essentially subjective, something like that. But I mean, there must be some condition on both sides. But anyway, this category is much bigger, in my opinion. And this is kind of finding some kind of section. I mean, so this category is much bigger category. And I mean, yeah, so this is kind of pullback functor. So whenever I have a bundle here, then I can pull back bundle a certain way, so obtain this new bundle here. And I mean, so when I consider, for example, moduli space of vector bundles on curve parabolic bundle, then this is usually Grassmannian bundle over this moduli space of usual vector bundle. So this has more structure and many more objects here in general.
And your theorem is like a explicit
Yeah.
interpretation of that same functor, but at the level of bundle.
Right. So we use this theorem to construct, to understand this. Both functor has very natural interpretation. Sense.
Is this similar to what Bauer does when he constructs explicitly the moduli space of parabolic bundles on a curve, via these elliptic bundles on elliptic surface?
Right. Exactly. So yeah, indeed. I mean, I think this theorem is, I mean, in the paper you just mentioned, I guess. I mean, how can I say? So Bauer identify, I mean, this certain vector bundles on this elliptic surface with the parabolic bundles on this curve. And this theorem is, okay, sorry.
It's like the Higgs version.
Sorry. Yeah, that's right. So the question was asking whether the relationship between this work and this Bauer's work, which relates the vector bundles on this curve surface and this curve. And exactly the answer is this is Higgs version of the result. And if I consider some vector bundle, vertical vector bundle, then this is what exactly Bauer did. And what Bauer did is he generalized this, he or she generalized this result for the case of Higgs bundle on this. So but we can also easily generalize this Jubes construction for Higgs bundle case. So anyway, we can make this theorem works for this larger category. Yeah, sure.
So this equivalence of categories that the power are not that is independent of how you chose H.
Yeah, H, they choose H to be sufficiently ample. Just that's the. I mean, if I choose my amplitude device to be sufficiently ample with respect to this vibration, then this result holds. Yeah. Of course, it's an interesting question. I mean, if we change this H, then what happened? And
H doesn't show up in the right hand side category.
Right, exactly. That's this H doesn't show up in the right hand side because in here H is just sufficiently ample divisor. Yeah. So meeting very positively for each fiber. That's the Yeah, thank you. That's very good point indeed. So it's an interesting question. I mean, if we vary this H in some way, then I don't know how to understand this in terms of this thing.
So you're saying if you vary it and if it stays sufficiently ample, then the category will be the same.
Yeah, right. Yeah, so indeed the H doesn't play. I mean, choosing H is not so picky. I just choose very ample H with respect to this vibration, then it works. Yeah. Okay. So, is there any other question?